Hello class. So now we've completed our unit on deductive logic, and we'll be moving on in the second half of this course to inductive logic and a bit of decision theory at the end of the course, which is still largely inductive but has more to do with games and setting up tables rather than the mathematical statistical equations that we'll be looking at for this section. So in this 9th video, I'm going to introduce inductive logic. We're going to talk about a couple different theories of probabilities. And then in the next lecture, I'll talk a little bit more about some other theories of probability. So what is inductive logic? I like to think of inductive logic as the logic of everyday reasoning. And why I think of it this way is because when we're doing reasoning in our everyday lives, when we're thinking whether or not I should take 8 south or 1100 south to get to campus, what I'm doing is weighing different probabilities. I'm saying, what's the probability that I hit the extra stoplights on 800 but have the faster speed, or alternatively have stop signs but it's a lower speed limit on 1100. And what I have to do is I have to balance and weigh the measurement of which of these options is going to be better off for my drive to work, to campus. And the way that I determine this in my reasoning is by probabilities. What's the probability of all of the different stoplights that they go red, right? And I show up late to class. I assume, given the amount of times that I've driven to campus before, that that's not going to happen. And in virtue of that assumption, I make it on the basis of some sort of evidence on my drives to school in the past. Now, this evidence operates as a statistical value from which I generate an intuitive kind of probability. And so I say, it's probably not likely that I hit all red lights on my way to campus. And insofar as I make this conclusion, or I make that inference on the basis of my past evidence, what I've done is engaged in inductive logic. And so for this unit of the course, what we're going to be doing is investigating that form of reasoning, which is different from deductive logic. So deductive logic, if you recall modus ponens, if P, then Q, P, therefore Q. Deductive logic is analytic, it's rigid, and it's structured. What we need are these crystallized atomic statements that tell us what certain conditions necessarily must be. If P, then Q, and P exists, therefore Q. But it's not always the case, and often pretty much always is not the case, that we have such crystallized truths that exist out in the world. There aren't just logical necessities floating around that we can use to practically reason our way through our everyday lives. Rather, we live chancy and risky lives. We live lives that are based on probabilities. Is it probable that I'll stab the back of my throat and need to go to the hospital when I brush my teeth? No. But there's still a chance, right? It's not the sort of necessary truth, like, of course that's not going to happen, that a deductive logic would require in order to be valid. Because validity requires a sort of airtight connection between the premises and the conclusion. Rather, with probabilities, what we're doing is determining the strength of an inference rather than its deductive validity. And in virtue of strength, what we find is, or weakness that is, that some inferences are more licensed than others. Though we can make any inference we like. I could be terribly afraid to brush my teeth in the morning on the basis of the very small probability that I end up having to go to the hospital for it. That would be silly, but that's an inference that I'm licensed to make, though it's a very weak inference. And again, this is the kind of reasoning that we use probabilities to measure and to determine. Okay, so when considering inductive logic, I've said the word a bunch of times, we're talking about probabilities. We're talking about probability theory. Now, this is something that you might have dealt with if you've taken any statistics courses or some math courses will touch on this as well, but largely inductive logic is the logical background to all of your contemporary statistics. We're not going to be looking at it through the statistical lens, but if you're interested, then those connections are there. And the main problem that we're going to have to be dealing with is what is a probability? How are we to understand probability? Because I could say, I'll probably get to school on time if I take 800 south. Likewise, I could say, I'll probably get lost if I walk up into the mountains. Or it's probably true that it's not raining outside because I can't see a cloud in the sky. You just have to take my word for it. But these are different ways in which we use the word probability. And now you won't have recognized it right now, but maybe at the end of the unit, coming back to this video, you will. All of those different statements use different forms of or definitions of probability. Now, if you do take an inductive logic class, 3400 I think is what it is, this is pretty much the problem that you deal with the entire semester. We're not going to be digging that deep in. We're just going to look at sort of we're going to scratch the surface of possible answers to this question, what is a probability? And so probability theory or inductive logic was developed by Blaise Pascal, who some of you might know as the guy behind Pascal's wager, which we'll be talking about towards the end of the summer session in the decision theory course or series of lectures. Now, Pascal was a French mathematician and scientist who really enjoyed gambling. And so he wanted to get better at it, and so he applied his mathematical mind to gambling and invented the very basics of probability theory. And your book, the textbook, calls this the classical theory of probability. For the sake of these videos, I'm going to call it frequentism. So frequentism is one way of interpreting what a probability is. And it does so in the following way. And I'll write the equation on the board and then I'll explain it. This is a probability according to frequentism, or at least the early classical form of frequentism. And what this says is that the probability, PR stands for probability, of some event, that event just is variabilized as A, equals the frequency of favorable outcomes, the number of times that A occurs, divided by the total number of iterations or test runs that have occurred. So let's say, for example, that I'm flipping a coin, right? Flip, flip, flip. And I want to say, what's the probability that I flip heads of this coin? So what I'm going to do, out of say like 100, the probability that I flip heads of the coin is going to equal, so let's say probability of heads equals whatever f is going to be over 100. So I'm going to flip the coin 100 times, so 100 will stand for n, and f is the number of times that the coin actually does flip heads. So just for the sake of making it easy, let's say that I flip the coin 100 times and it's the case that I flip 50 heads. So the probability of getting a head would be 1/2. Now, this may not be the case. I'm sure that if I flipped a coin 100 times, I would not get exactly 50 heads and exactly 50 tails. And this ends up being one of the problems with our early form of frequentism. But it is a helpful tool, early frequentism, that this equation is simple and it's easy, and it shows us that the probability of some event occurring is just the frequency of its occurrence in all of the different possible circumstances in which that occurrence could arise, right? So, for instance, the frequency that I draw a jack from a deck of cards in a million different draws is going to be about 1 over 52, right? Because there's 52 cards in a deck of cards. And one of those is, 4 over 52. 4 of those are jacks. Now, the frequentist view has some shortcomings. And this is described in your book. It's section 11.1. And it happens on page 587. And these shortcomings are that this version or this interpretation of what a probability is requires two assumptions. So first, we have to assume that we're able to take all of the outcomes into account in measuring a probability. So I have to be able to take into account every single number of n's that's occurring if I want an accurate probability. So say I want to know the probability of flipping heads on this particular coin, right? And so I flip it 100 times. But somebody else has also flipped it before, and I determine the probability based on my 100 flips, but I don't know all of the flips of the previous coin flippers of that particular coin, and so my probability is going to be limited to my observation, my certain number of tests, and so it's going to be indeterminate with regard to the rigid rules of this particular equation. That is, the probability will be indeterminate. I can determine what the probability is that I've seen, but the actual real-life hard probability that exists in that particular coin for its chance to flip heads is something that would require all of the iterations to be taken into account, though I haven't taken those. I'm not able to take all those into account. Now, this isn't always a problem. There are certain statistics and certain measures that have only existed for the last 20 years or so. For instance, you could measure the probability of a person's joining Facebook on the n of all people with access to the internet, and then the frequency of how many of those people have Facebook accounts. Like if it's 3 billion people have Facebook accounts and 7 billion people have access to the internet, that would give us a probability where we have all of the n available to us. But again, there are certain edge cases, and maybe not even edge cases, but big problem cases like the coin flip. What's the probability of that particular coin flipping heads, where we don't have the total number of n cases and so aren't able to determine a probability right away. Now, okay, so that's one assumption that we sort of have to set aside if we're going to accept this classical frequentist or classical, let's see, what does he call it? Yeah, the classical theory of probability. The second assumption is that we need to assume that all outcomes are equally probable, that we can't determine what a probability is if there's some sort of funny business in the play, right? So, for instance, say that I run 50 tests of my 100 with the coin, and over the course of the 50 tests, I begin to say I'm flipping on a beach, right, on the wet sand and letting the coin hit. And for the first 50, it's just about fine, but then a wave rolls up, and all of a sudden, my coin starts picking up sand. But it's only picking up sand on one side of the coin, one face. Now the sand is going to make the coin land more likely on that particular face. And so halfway through my tests, what I've done is I've changed the conditions of the way in which the probability is measured, because the outcomes of the coin flips is dependent upon the coin maintaining a indifferent, right? That's going to be our technical term, but a constant and untouched sort of version of itself. But as soon as the sand starts to attach to it, we add a bias or a weight to the particular way in which the coin is flipping, and thus we change the outcomes. So we can't measure weights for different occurrences under this simple form of probability. The probability assumes that every test, every n, is equally weighted against every other n. That there's an equal likelihood of any outcome of heads or tails in the case of the coin, of the 4 out of 52 for the case of pulling a jack from a deck of cards, that every test has that same likelihood, and that's the likelihood that we're measuring in virtue of the frequency. Now, this is a big assumption, and it's one of the reasons, and in fact, it's probably the most important reason that has led modern statisticians and modern logicians to deviate from this basic form of frequentism and revise the theory with what our book calls the relative frequency theory of probability. And so I'm going to get rid of this. So for the sake of this video, I'm going to call this relative frequentism, though your book calls it the relative frequency theory of probability. It's pretty much the same stuff. It is the same stuff, just the name's similar. Anyways, our relative theory of frequentism for probabilities interprets probabilities as observed events. So not events that are completely measurable, that we know all of at any given time. We know the entire range of a frequency of a set of outcomes. Rather, the relative theory doesn't take the absolute measure, but rather the observed measure. And so our interpretation of a probability of some outcome becomes the probability of A equals the observed frequency, or the observed favorable outcomes, divided by the observed number of tests. And so this resolves the two problems that were raised by the assumptions that were present in our classical theory. The relative probability interpretation doesn't treat probability as something theoretical, that we can just know all of that particular coin's flips through all of history, or that we can't measure the weight of certain tests and outcomes. Rather, all of that's taken into account by our little O subscript, because what we're doing is we're just measuring the frequency of an outcome that we've observed. And so we're not indicating that that coin has a 50-50 chance for heads. Rather, what we're indicating is that the probability of that coin being heads on any given flip is 50% or 0.5 given what I've observed or what we've observed in flipping the coin itself, right? So this is the form of probability that you'll look at in a stats course that will be sort of your foundation for almost all empirical scientific data gathering. And it has really serious problems. It has big problems. That when we say that a probability is a frequency at all, that it's some number of events, favorable outcomes, divided by a number of iterations or occurrences. Even if we indicate that the favorable events and the occurrences are observed rather than static and theoretical, we still only understand probability in terms of a number of events. That this kind of equation and this interpretation of a probability can't give us the probability of a one-off event. It requires a frequency. And so if I were to say, what's the probability that okay, so imagine that I'm out for a walk in the woods and I get lost, right? And I think I might sort of have a sense of my direction, my bearing, but I don't really know. And this is a single event. I'm not going to get lost again. I haven't been lost in this particular forest before. And I think to myself, what's my best chance of getting home? What will increase my probability of returning home? Do I go with my hunch, or do I follow the sun until I find civilization? This is a sort of one-off event. It's not a frequency of occurrences that can still take a probability under the interpretation of frequentism, because what we need to do is measure all of the different times that I got lost in that particular forest and followed the sun or my hunch about the direction. Rather, we have a single one-off event that still I would, in that situation, want to call an event that has to do with a probability. That it's more probable that I make it home if I follow my hunch than if I go out of the forest. Alternatively, a more simple example, if I have a coin and I say I just minted it, right? Like I work at the US Treasury and I mint a coin. And I say, what's the probability that this coin flips heads on the next flip? And so I flip it. Our frequentist theory can't tell us, because it's only going to give us, it's either going to be 0 over 1, which is undefined, right, because it flipped tails, or it's going to be 1 over 1 and then tell us that the coin absolutely flipped heads, right? That the probability that that coin flipped heads because I flipped it one time and it flipped heads, that the probability is 1, or there's a 100% chance that it flips heads, is just wrong, right? We don't think that probabilities are just the number of times that a coin's been flipped, but we think, no, there's something else going on, right? That even if the coin was just minted, and I want to know the probability of that particular coin's flipping heads, I still intuit that there's a 50-50 chance. But that intuited 50-50 chance can't be captured by our frequentist theories of probability. And so what we do as inductive logicians, now all of you are inductive logicians too, or will be after this unit, I suppose, is we introduce a new way of interpreting probabilities, which will have its own problems as well. This is a really fantastic way of interpreting probabilities, but again, it has its shortcomings. And so will our next version as well, which we'll call the subjectivist interpretation of a probability. And if this is a scientific and empirical form used in statistics and data gathering, our subjectivist form or interpretation of a probability doesn't involve the same sorts of problems, because it can measure the probability of one-off events and satisfy some of our intuitions about probability, like the newly minted coin having a 50-50 chance or a 0.5 probability of flipping heads on a first flip, because it has to do with us, that we interpret them as degrees of belief. And that we'll talk about in the next lecture.